Welcome back, ladies and gentlemen. So, last time we spent our efforts learning how to do the whole formulas to names and names to formulas, right? We learned how to turn things like aluminum and chlorine, three of them specifically, into aluminum chloride with that IDE ending. We also learned how to go backwards from that. We learned how to take magnesium phosphide, right? Ide meaning that this is an ion, and turning it into Mg3P2. Why 3 and 2? Remember, we talked about that, and we saw that magnesium is 2 plus, and phosphorus is 3 minus. So in order for these to equal each other, I'm going to have to turn them both into 6. 6 plus and 6 minus. And the way I do that, multiplying this one by 2 and this one by 3, leading us to Mg3P2. Now, the thing is, all of these examples that we're working with follow a very predictable pattern. They all follow the pattern that we find in the bulk of the periodic table, or I should say the two ends, this side and all of this side. This is a little bit tricky, though. Why? Well, there's this entire section in the middle that we're not touching. And that's what we're going to do right now. The entire section in the middle is a little bit weird because it doesn't follow the same pattern as the rest. There's still a pattern, but it's not as easy. It's not as simple as the pattern that we see in the other compounds. You see, the middle of the table, as we've discussed, is the transition metals. They are so called because they are a way to transition or to move from the pure metals over towards the metalloids on the far side. They transition across the bulk of the table. You'll also, of course, remember that as we discussed, the number of spaces in a particular row tells you the maximum size of that shell. We had our 2s, we have 2 8s, and then down here we've got our 18s. 18 is quite a bit bigger, so there are more options when it comes to the transition metals. But unfortunately, it's not as simple as we saw previously. We can't just count how far we are from the end and just assume that's how many steps it is, right? It's not like iron here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. From the end is going to be 10 plus. It's not how that works. Not at all. And this is the first big problem here, is that the elements in the transition metal area do not follow a set pattern. In point of fact, they tend to come in a variety of different flavors, like flavors of ice cream. So if we once again look at iron as an example right here, Fe, iron comes in two big flavors. In the old days, back when iron was called ferrum, iron was divided based on the way you'd pronounce the word. There was ferrous and there was ferric. Ferrous and ferric each had a different charge, a different ion design. But that was really problematic because it meant that you had to not only memorize all the different elements, you had to memorize 2 or 3 or 4 names for the different elements. That's a lot. I mean, admittedly, in the old days, the periodic table wasn't quite as big as ours is now. Ours, at this exact moment, goes up to number 118. But I still don't want to have to do 2, 3, or 4 times as many. That's 2, 3, or 4 times more work than I want to do. So, thankfully, a German chemist by the name of Alfred Stock managed to come up with a much better way of keeping track of the different types of charges. It got named after him, the Stock system. And the very simple idea was, well, the Romans were pretty cool and they were pretty good at this whole funny names and stuff, but you know what else they were good at? Roman numerals. And we're going to use those Roman numerals to explain and explore the different flavors of ions. Now, before we go any further, all of these ions are metals, all of them, which means they're all going to be positive. Right? There are no negative transition metals. It just doesn't happen. So on the very plus side, that makes this a lot simpler, right? Everything that we're going to deal with is going to be located on the left side of the equation. On the downside, there is still some variation, and we kind of need to know how to do Roman numerals in order to make sense of this. Now, most people have seen Roman numerals, but not everybody, so just a quick refresher. Roman numerals are the way that we used to write numbers back before we figured out Arabic numerals from the Indians. Yet just, things move around. So these were the Roman numerals. The first three are pretty easy. 1, 2, 3. 4 is 1 less than 5. 5 itself is V. 6 is VI. 7 is VII. 8 is VIII. And I've now run out of space, so I'll put the last two over here. 9 would be IX, and of course X for 10. So each one of these corresponds to sort of a basic idea. We've got our 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Each one of these corresponds to, a number, and each one of these can be used in substitution of a number in any kind of discussion or formula that we're going to write. So, for example, let's say I've got a particular flavor of copper, right? So, in the old days, this would have been called cuprous, or maybe cupric. I'm not sure which one it would be. And I want to be able to discuss it using the stock system. Instead of taking our good old cupric here, we would instead go Cu2+. So that's what cupric would be. But instead of writing the word cupric, because I don't want to have to memorize a whole bunch of languages, you don't want to have to do that either, we would instead keep it very simple, and we would just simply say that this is copper 2. The 2 in this case, the Roman numeral 2, is telling us the charge of the copper, the flavor of the copper. That's for cupric. What about cuprose? That would be Cu+. So using the stock system, that becomes copper 1. You'll notice that I'm putting it after the word copper. I'm putting it in brackets. I did decide to use capital Roman numerals. You don't have to. You could just use lowercase if you want. But that's the basic idea, right? So if I put in here, say, Fe3+, you don't have to come up with what that word would be. Instead, you just simply look at it and go, okay, so that's going to be iron, and it's iron 3. So 1, 2, 3. Brackets. And we're done. All right, fine. Let's go a little bit deeper. All right, that's the basics, but how do we use this? So let's say that I've got FeO. FeO, very simple here, right? Iron oxide, right? It's iron, Fe, oxide, because it's oxygen. But what type of iron is it? Can we figure that out? Well, we know what the charge on oxygen is. It's always the same. It's always 2-, because oxygen is in one of the families that is predictable. The iron is less predictable, but look, I've got one of each, which means this one and this one have to be equal. If these have to be the same, and oxygen is 2-, iron has to be 2+. So this becomes 2 positive. If that's the case, when I write out the full name, I would go iron oxide, and this is iron 2 oxide. All right? That's it. That's all you have to do. In the previous section, we didn't write anything about the numbers, but here we do, but only for the metal, because only this guy has something weird about it. It could be multiple options. What do I mean? Well, let's take another look. We're going to go the other way. What about iron 3 oxide? Right? How would we write that? Well, we know that it is iron, Fe, and we know that it is oxide, O. So far, pretty easy. But now we have to write the numbers. That's always the hard part. So we know the oxygen, that one's always the same, 2-. And the iron, we don't know what it is because it's not always the same, but we do know what it is because they tell us. It's right there. It's a 3. So I'm going to put 3+. Then all I have to do is make these two equal to each other. I've got a 3 here and a 2 here. Well, in order for that to balance, it's got to be 6, which means that this one here is going to be multiplied by 2, and that one's going to be multiplied by 3. So if I write it out nice and simply with no extra clutter, Fe2O3. Ta-da! That would be iron 3 oxide. So you'll see, iron 2 and iron 3 oxide, both are made of iron and oxygen. The difference is how much there is. Now, why is that supercritical? Well, it's not actually supercritical. I mean, not for you. You guys aren't, engineers designing buildings or anything. But understanding that iron behaves differently depending on which particular type of iron it is, that is useful for people who are working with iron, like anyone who's building anything ever. Ever. We use a lot of iron and steel these days, guys. Anyway, that's it for the stock naming system. It's very straightforward. It comes down to you naming the thing you're using. There's just one little problem that most students run into, is that, let's do another one. Let's say I go with copper 2 oxide. A common thing that I will see students do is that they will go Cu2O, because they assume that the 2 must correspond to the number of copper, not the flavor or the strength or the value of the copper. So this is just wrong, because it's not 2 as in there are 2 coppers. It is 2 as in the copper has a worth of 2 compared to the oxygen, which has a worth of 2. So this would just be CuO, and that's it. Done. So that's the only real tricky one that students will do on a regular basis, is that they will get copper 2 and assume that it's the 2. They'll hear iron 3 and they'll assume there are 3 irons, because there is a 3 in here, so it's not unreasonable. It's just in the wrong place. So that's the only part that you need to be careful about. Now, in the case of some of these questions, right, you were able to figure it out. You were able to deduce what type of iron it is based on the other numbers you had around it. But what happens if you don't have enough information to be able to deduce everything, to figure it out by looking at it and using your amazing chemistry brain? Well, in that case, what you would do is you would pull out your periodic table that I provided you. You will flip it open, and you will discover that there is a chart that tells you a bunch of different flavors of ions, especially in the middle area here. So for example, here it tells me that cobalt next to iron can be 2 plus or 3 plus. It tells me that nickel could be 2 plus or 3 plus. It tells me that copper could be 2 plus or 1 plus. So it gives me a sense of all the different flavors. Now again, I will remind you, you will be given this periodic table on your test, which means, once again, you have all the answers if you know how to read it. But that comes with practice. That's about it for this. You guys just need to do that practice now. It's a simple one to start with. But, take a look at it. And I will see you guys next time.